Good day, learners. Welcome to our physical sciences lesson. My name is Aminim Kize. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. Right, grade 11s, our focus today is still on knowledge area mechanics, and then under mechanics, the focus is still on Newton's law or Newton's laws and application, right? But our focus today will be more on Newton's third law, right? And also Newton's law of universal gravitation. So under Newton's third law, our focus will be stating the law in weights, correctly so, and also identify the action-reaction pair of forces, list the properties of action-reaction pair of forces, right? And when it comes to Newton's law of universal gravitation, our focus will be one, stating the law in weights and then showing the relationship, using graphs, all right, and solve problems using the equation F equals to G m1 m2 over r squared, and then differentiate between weight and the mass, and also calculate weight using the equation weight equals to mg, and then explain the term weightlessness. So it's what we are going to focus on today. So this is the content that will be covered today. It's still on Newton's laws and application, and then the focus is more on Newton's third law of motion and Newton's law of universal gravitation. Learners, this is our important data sheet, right, where we have all the constants. So familiarize yourself with it, okay? Your acceleration due to gravity, which is what we are going to deal with, and we've been dealing with that even before when we calculate the magnitude of the gravitational force, or the weight, which is given by mg, right? So that g is acceleration due to gravity on planet Earth, which is 9.8 meters per second squared. And then the gravitational constant, which is what we are going to look at today, right? And the Newton's law of universal gravitation, Re, which is the radius of the Earth. And then K, we are not going to focus on K because we haven't touched on Coulomb's law. We'll look at that next week. And then the speed of light in a vacuum, right? Again, that's not our focus. Even the E there, the mass of an electron, there and there we can deal with that, the mass of an electron, right? And also M. So M, capital letter M, there's the mass of what? Of the Earth. So these are the important, constants that we are going to deal with today. Is this one, this one, this one, this one, and this one, all right? So there's no need to memorize those values, okay? They're there on your data sheet. Whether you're writing a formal, informal exam, it doesn't matter. It's all right to have, the data sheet. So you'll be given the data sheet. So you'll be given these constants, all right? Okay, then the equations, important equations when it comes to Newton's laws and application, your F net equals to MA, especially when we are dealing with Newton's second law, calculating the maximum static friction, kinetic friction, and then this one, weight, which is what we are going to deal with, and then this equation of calculating what? The gravitational force, which is F equals to Gm1 m2 over d squared or r squared, and then G equals to Gm over what over r squared. So our focus is here today. These are the equations that we are going to deal with moving forward, right? Then maybe just to recap on what we did last week, it was Newton's third law. What is important to state that law as it is, okay? It states that when object A exerts a force on object B will simultaneously exert an equal an oppositely directed force of equal magnitude on what? On object A. So that is how we have to state Newton's law, or Newton's third law of what? Of motion. So when body A exerts a force on body B will simultaneously exert an oppositely directed force of equal magnitude on what? On object A. So that is how we have to state, Newton's third law of what? Of motion. All right, then I think another thing that we indicated last week, right, is the issue of the action-reaction pair of forces. You must be careful there. It's not just any pair, but it should be the pair of what? Of forces. And then one force will be the action, the other one will be what? The reaction. So it's action-reaction pair of what? Of forces, okay? So what is important here, especially when it comes to listing the properties of action-reaction pair? Right, one, when it comes to Newton's third law, it states that when object A exerts a force on object B, right? So here we are having how many objects? Two objects exerting forces on what? On each other. So what is important is that those two forces, they're not exerted on what? On the same object, although they're equal in what? In magnitude, acting in opposite directions, but they're not exerted on what? On the same object. That is very, very important. When it comes to Newton's third law, when you talk of action-reaction pair of forces, you should know, yes, we understand they're equal in magnitude, acting in opposite directions, but another thing which is very, very important is that those forces, they're not exerted on the same what? On the same object. That is very, very important. Although they're equal, but they're not exerted on what? On the same what? Object. So when it comes to the properties, what is important? One, the forces are equal in what? In magnitude. That is one of the properties. The forces are equal in magnitude. Forces are acting in opposite directions, but even if they are equal or acting in opposite directions, what is important is that you should know that those two forces, they are not exerted on the same what? On the same object. So those are the properties of what? Of action, action-reaction pair of what? Of forces. Forces are equal in magnitude. Forces are acting in opposite directions, right? But those forces are not exerted on the same what? Object. So they're exerted on different what? Bodies or different what? Objects. That is very, very important. Okay. For example, we have used this example last week to explain the issue of action-reaction pair of forces, right? You have a block on top of the table, all right? So when you talk of action-reaction pair of what? Of forces, one here, the table and what? And the block. On top of that what? Of that table. Then we have a force exerted by what? By the table on what? On the block, and it goes together with what? The force exerted by what? The force exerted by the block on what? On the table. You can see it's negative there. Why am I putting that negative? Is that as much as they're equal in magnitude, but they're acting in what? In opposite what? Directions. So this is a pair of what? Of action-reaction pair of what? Of forces. So force T on B and force B on what? On T, acting in opposite what? Directions. So properties, they're equal, okay, in magnitude, acting in opposite directions, and they're exerted on two different objects. They're not exerted on the same what? Object. So those are the properties of action-reaction pair of what? Of forces. All right. So force T on B and force B on what? On T. Though that is action-reaction pair number one. All right. So our focus is this scenario, learners, is that there's a block on top of what? Of the table. So there's a force exerted by the table on the block. T stands for the table there, and then B stands for the block. And then the action is force table on the block. And then the reaction force will be force what? Block on what? On the table. Okay, so that was our focus. Those two objects that are in contact, which is the block and what? And the table. Force exerted by the block on the table, that is action what? Force, and then force exerted by the table on what? On the block, that is the reaction what? Reaction for reaction what? Force. And then this is what we call action reaction what? Pair of what? Of forces. Okay, these are action reaction pair of what? Of forces. But another thing that we need to not to forget is in most cases, learners, what they do when it comes to action reaction pair of forces, they will only focus on objects that are in contact only. The forces exerted by objects that are in contact. All right. For example, in this case, what is in contact with what? The block and the table are in what? Are in contact. So there's a force exerted by the table on the block, and then the reaction with the force exerted by what? By the block on what? On the table. So they only focus on what the forces exerted by objects that are in contact, and they forget that there is also what? A non-contact force that is always there, right? There's a non-contact force that is always there, and then that non-contact force is gravitational force or weight. Okay, so there's a non-contact force which is always there. So for example, by now you know how to draw free body diagrams, all right? Or you know how to draw force diagrams. So if they can say draw a free body diagram indicating all the forces acting on the block, right? One of the forces that will be there, like it or not, it should be what? The gravitational force, all right? And then if they can say draw a free body diagram indicating all the forces acting on the table, right? One of the forces that will be there, like it or not, right, it's going to be what? The gravitational what? Force. So when you deal with action-reaction pair, let's not just focus only on the forces exerted by objects that are in contact. Let's not forget the non-contact force, which is always there, which is the gravitational what? Gravitational force. For example, when I'm looking at this, there's a block, right? So there's a force exerted by what? By the block on what? On Earth. Okay, you can say on Earth or what? Or weight or gravitational force. Okay, right? Which goes together with the force exerted by what? By Earth or weight on what? On what? On the block. So this is another action-reaction pair of what? Of forces. Let's not forget a non-contact force, which is gravitational force. For each and every object, that force is there. All right, I'm sitting on top of the chair, right? So there's a force exerted by me on the chair. There's a force exerted by chair on me. That is action-reaction pair, right? That is contact, okay? But again, I have my own gravitational force or weight, right? So there will be force exerted by weight on me, and then it goes together with the force exerted by me on what? On weight. That is another action-reaction pair of what? Of forces. Very, very important. Let's not forget a non-contact force, which is weight, when we are dealing with what? Action-reaction pair of what? Of forces. Same with the table, right? So if they can say draw a free body diagram indicating all the forces acting on the table, one of the forces that will be there will be the non-contact force, which is your gravitational force, all right? So there's a force exerted by what? By the table on Earth. It goes together with what? The force exerted by the Earth on what? On the table, right? So that is another example of action-reaction pair of forces. Very, very important. In most cases, we only focus on what? On contact. All right, let's not forget that there are also non-contact forces, and that non-contact force that we are referring to, it should be weight or the gravitational what? Force. Very, very important. Okay, then those are action-reaction pair of what? Of forces. Action-reaction pair of what? Of forces, right? So let's not just focus only on what? On contacts, okay? Even there's remember there's also what? A non-contact what? A non-contact force. For example, looking at this, right? So I'm not going to do calculations here, all right? But now what is important? What is important when it comes to the properties of action-reaction pair of forces? What I said to you is that, okay? For example, you can see object A and object B, they are in contact here, all right? So there's the action-reaction pair of forces will be force exerted by A on B. It goes together with the force exerted by B on what? On A. That is a pair, right? So action force will be the force exerted by A on B, right? And then the reaction force would be the force exerted by B on what? On A. So that is action-reaction pair of what? Of forces. And what I was focusing on there is only what? The forces exerted by objects that are in contact. A on B, B on what? On A. That is action-reaction pair of forces. So if they can say I list the properties of action-reaction pair of forces, what I will say, one will be these forces are equal in magnitude. All right, so look at the free body diagram here. Look at the free body diagram. Look at the force exerted by B on A. So that force is exerted on A. So it's on A, right? Okay. Then another reaction force, because that one was the action, the one of B on A, and then the reaction will be what? A on B. So A on B is this one. Check the red arrows there, right? This one and this one, right? You can see that this is the force exerted by A on B. This is the force exerted by what? By B on what? By B on A. Or maybe we can draw that, okay? So I just want to draw the forces. If this is object A, and then this is object what? Object B. You can see they're in contact there. There is a force exerted by what? By B on A. So it's on A. So B is pushing A to the left, right? So there's a force exerted by B on what? On A. Force exerted by B on what? On A. Then the reaction force will be the force exerted by what now? By A on B. So that force is on B, all right? So A is pushing B to the right, okay? So this is the force exerted by what? By A on what? On B. So what is important is that, one, these two forces are equal in magnitude. If this one is 54 newtons, even this one will be what? 54 what? Newtons. So they're equal in what? In magnitude. Two, they're acting in opposite what? Directions. You can see that your B force A on B is to the right, and then force B on A is to what? Is to the left. So they're acting in opposite what? Directions. But another thing which is important, these two forces that are exerted on different objects, or on different two what? Objects. This is object A, this is object B. You can see they're exerted on different what? On different objects. That is very, very important. Yeah? So here, again, learners, let's not only focus when a question wants us to talk about what? Action, reaction, pair of forces. Let's not only focus on contact. Yes, it's where we have to start, I guess, right? So A on B, B on what? On A, right? But again, if they can say draw a free body diagram indicating all the forces acting on A, for example, this one, this is A. Can you see that FG is there, right? Draw a free body diagram indicating all the forces acting on B. Here it is. You can see FG is what? Is there. So let's not forget that non-contact force, all right? So action, reaction, pair of forces, it will be force exerted by what? By A on F, and it goes together with what? Force exerted by F on A, right? Another one, when you are focusing on what? On B, force exerted by B on F, it goes together with what? F on what? On B. Or force exerted by F on what? On B. Or force exerted by weight on what? On B. Force exerted by weight on what? On B, right? So those are action, reaction, pair of what? Of forces, right? So let's get a question on action, reaction, pair of forces. A car is traveling along a road. The driver has his seat belt on. The driver sees an obstruction in the road ahead and suddenly applies the brakes, okay? So now the question is, an action-reaction pair is the force of the action-reaction pair is the force of the seat belt on the driver, and which one, right? So here, first thing that you need to do, check when it comes to the reaction, the action force, right? The objects that are involved there, okay? There is a seat belt and the driver, right? So even when it comes to reaction, there must be what? A seat belt and what? And the driver. So if your action is force seat belt on driver, then the reaction will be force driver on. So it's other way around. Is this the force driver on what? On the seat belt. Okay. So first thing that we need to do, if you're given a question like this one, identify the objects that are exerting forces on each other. Is the seat belt and the driver. All right. So the action is the force exerted by the seat belt and the drive on what? On the driver. Obvious, it should go together. Force seat belt on what? On the driver. It's what is given, right? And this should go what? Together with what? Force driver on what? On the seat belt. So this is action-reaction pair of what? Of forces. So when you look at option A, driver on the seat, can you see the objects that are there? It's seat belt and the driver, not a seat, ne? So it's not the same objects that are used here. So obvious, this one is out. So this is fine, but it's the seat instead of the seat belt. Okay, so A is out because of that. Wheels, road. Initially, did we have those two objects? No. We are given seat belt and the driver. So wheels, road, we don't care. So it's out already. All right. So I'm looking at option C. Objects, it's seat belt and the driver. And then when it comes to C, driver and what? And the seat belt. So this one, we can check it. But for now, we are not sure whether it's correct or not. But because of those two objects that are involved there, or that are exerting forces on each other, right, then we can go for C. But we need to check the last one. The last one, seat belt on seat. This is out. Yes, there's a seat belt, but not the seat. It should be what? The seat belt and what? And the driver. So force seat belt on driver. Okay. So force seat belt on what? On driver. It's what is given. And then the reaction force will be the driver on what? On the seat belt. So the correct answer there will be what? Will be C. Right. Then let's move to Newton's law of universal what? Gravitation. When it comes to Newton's law of universal gravitation, first thing that we need to do is to make sure that we state that law correctly. In most cases, learners, they lose marks here, although in most cases it is marked independently. But with other examiners, they will say 2 marks or 0. So which means that we need to state it correctly. We shouldn't actually omit any key weights when it comes to stating this law, which is the law of universal gravitation, right? So when it comes to this law, right, any two bodies in the universe exerts a gravitational force on each other, right? And then this force is directed along the line joining the two bodies, and then the magnitude of the force is directly proportional to the product of the two bodies masses, and inversely proportional to the square of distance between their centers. So here, when it comes to our examination guidelines, so allow me to go back. Ne? When it comes to our examination guideline, this is how we have to state Newton's law of universal gravitation in what? In weights. Each body in the universe attracts every other body with a force that is directly proportional to the product of their masses. It's not just the product, but it's the product of their what? Masses, and inversely proportional to the square of distance between what? Their centers. So this is how we have to state Newton's law of universal what? Gravitation. Each body in the universe attracts every other body with a force that is directly proportional to the product of their masses, and inversely proportional to the square of the distance between what? Their centers. Then in symbols, F is given by G m1 m2 over what? Over r squared, where G is the gravitational constant. It's a constant. So where do we get the constants? From the table of constants in our data sheet, right? So, and what is that value? And there's no need to memorize it because it's there on your data sheet, right? So G is 6.67 times 10 to the power negative 11 newtons square meters per kilogram squared. Okay, then that is the gravitational constant, capital letter G. So please, let's not confuse capital letter G with small letter g. We are used to small letter g, but there's also capital letter G, which is known as the gravitational constant, and its value is 6.67 times 10 to the power negative what? 11. So in symbols, they're saying in words, everybody in the universe attracts every other body with the gravitational force that is directly proportional to the product of their masses, and inversely proportional to the square of the distance between what? Between their centers. So I've talked about G. What is F here is the gravitational force, which is measured in newtons. And what is M is mass of an object, or mass of object 1. And then this is mass of object 2. So mass is here is measured in what? In kilograms. And then what is R? Very, very important. R is not the what in this case, the radius. And let me put it nicely. It is the distance between their centers, right? So for example here, we are given what the Earth, right? So we are given the Earth here, right? And then we are given what? This object. So when they talk about R, is from the center of the Earth to the center of this object. That will be our distance R, which is measured in what? In meters. Okay? So R is the distance between their centers, right? So when they set questions, just to check if you understand the meaning of R, they will give you maybe, for example, the Earth, right? And then object. Let's say just object what? Object A. And then this is what? The Earth. And then they will just give you what? The distance from the circumference, or the distance from the surface of the Earth to the center of this object. Yeah? Right. So when you do your calculations, you need to be careful, especially when it comes to the issue of R. F is given by G M1 M2 over what? Over R squared. This G is the constant 6.67 times 10 to the power negative 11. This M will be mass maybe of object A, and then M2 will be mass of the Earth, or M is, it doesn't matter. The order does not affect the answer. All right. So, but when it comes to R, learners, please be careful. You need to check this. Are you given the distance from center to center? Right? If it's like that, it's fine. You just substitute by that value. But in other cases, for example, in this scenario, is from the surface of the Earth to the center of this object, right? So you can say this is your R, right? Your R is from the center to the center. Center to the center. So that is going to be what? Your R. So what is it that you need to do? It's going to be your GM1 M2 over what will be your R? Your R will be this distance, right? From this, from what? From what? The center to center, which means that here you need to add the radius of what? Of the Earth for you to get the distance from center to what? To center. Please be careful when it comes to R. Read your statements carefully with understanding so that you'll be able to tell whether you are given R or you have to do something about R. For example, in this situation, they were given, or we are given what? A distance from the surface of the Earth to the center of object A. So your R will be from center to center. So where are you going to get this distance? RE, radius of the Earth, is there on our data sheet, right? So it's what you need to add when it comes to your R. Very, very important. Yeah? Right, then, according to the law, right, Newton's law of universal gravitation, right, every body in the universe attracts every other body, right, with a gravitational force that is directly proportional to the product. So product, they are talking about what? You have GF equals to GM1 M2 over what? Over R. So product, they are talking about what? M1 multiplied by M2. All right? So it's directly proportional to the product of the masses. Okay? So here we can even show that relationship. So F directly proportional to the product of what? Of the masses. We can even show that relationship using a graph. Okay? So a graph that shows direct proportionality will be a straight line starting from the origin. Okay? So I'm having F and product of the masses. Hence here I'm having kg squared because this is kg times kg. Therefore there I will have what? Kg squared. So this is not F versus m, but this is F versus the product of the masses. Very, very important, okay? So gravitational force, it is directly proportional to the product of the masses. So which means that when you increase the product of the masses, what happens to the gravitational force? Gravitational force also increases. So your gravitational force depends on the product of the masses. Very, very important, okay? So this is your dependent variable. This is your dependent variable, which is the gravitational force or force. This is the independent what variable. Okay, right. Then this graph, we can see it shows a direct proportionality between what gravitational force and the product of what of the masses. So what it says, it means that if the product of the masses increases, what happens to Fg, which is your gravitational force, or F, which is just a force, we can say it's a force, but you should know that we are talking about the gravitational force. Gravitational force also what increases with the same factor. Okay, so this graph shows direct proportionality between F and product of the masses. So if the product of the masses increases, what happens to gravitational force? Gravitational force also increases with the same factor. So in this graph, they can ask you to give them the variables, your dependent variable. You should know that your dependent variable is always along the vertical axis. In this case, our dependent variable is the force, and then your independent variable is always along the horizontal axis, which is what we call x-axis when it comes to our mathematics, right? So the product of the masses here is our independent what variable. It's not the mass, but the product of the masses is our independent what variable, right? So what must be controlled here, right? So you need to check when it comes to this equation. What is your focus? Is this versus that? So they need to keep this constant. So the what should be constant here would be what controlled. It should be what the distance between what the centers. Okay, right. Then another secret for graphs is the area and the gradient, right? So they can say, okay, what is the dependent variable, right? According to the graph, what is the independent variable, controlled variable, and the physical quantity now represented by the gradient of this graph. Very, very important. Physical quantity represented by the gradient of this graph. When it comes to physics, I hope all of us were aware that the secret for graphs, except asking you to give them the dependent, independent, the controlled, you know, another secret is the area and the gradient, right? And you'll find scenarios where there is a physical quantity represented by the gradient. There's no physical quantity represented by the area. Or in other graphs, you'll find that there is a physical quantity represented by the area under the graph, but there is no physical quantity represented by what? By the gradient. So in this case, there is a physical quantity represented by the gradient of this graph, all right? So where should we start to get that physical quantity? You can see that, learners, this is a straight line. This is what? A straight line. So if this is a straight line, we know the equation of a straight line when it comes to our mathematics, all right? It is y equals to mx plus what? Plus c, okay? So your y, m is your gradient, and then c is your y-intercept, okay? So in this case, your y, it's f, which is this part, right? Your x, it's what? It is the product of the masses, right? Then check the equation. Where you have f, m1, m2, there is only one equation. It's f equals to g m1, m2 over what? Over r squared, okay? What are you supposed to do? You have to manipulate this equation in a form of y equals to mx plus c, making sure that your y here should be what? It should be the force. Your x here should be what? The product of what? Of the masses. Okay? So let's start. I'm having f g m1 m2 over r squared. Already f, it's my y, or the subject of what? Of the formula when it comes to this equation. So there's no need for me to change it. Okay? So now what am I looking for? X. My x should be what? m1 m2. How am I going to do that? F is given by what? G over r squared m1 m2. Right? So this is the same as g m1 m2 over r squared. Ne? But now I just want us to be able to see that this is y, this is x. Our y should be f, and then our x should be what? Should be the product of the masses. So this is y equals to mx. My y is f, this is correct. And then my x here is what? Is m1, m2. This is also what? Correct. So what represents the gradient here is g over r squared. So you can see g over r squared represents the gradient of what? Of this graph. So the gradient of this graph represents g over r squared. So can you see that you can use the gradient of this graph to get the distance between the centers, right? For example, if you are looking for the gradient, you need how many points? 2 points. Let me just give you those points. Let's say here, obvious, this is the origin is 0 is to what? Is to 0, right? So let's say here we are having what? 5 times 10 to the power what? 3, obvious newtons. And then here, what are we having here? We are having what? M1, M2. So M1, M2, let's say it's 1.2 times 10 to the power what? 4, okay? Then this point will be 1.2 times 10 to the power what? 4 is to 5 times 10 to the power what? 3. Then this one will be 0 is to what? Is to 0. We are using the gradient to get the distance between the centers, right? So I hope you saw how we got that g over r squared. This is a straight line, right? If it is a straight line, we are doing maths. The equation of a straight line, it's y is equals to mx plus c, right? Then our x, our y according to this graph should be f. As you can see, our x along the x-axis or along the horizontal axis, our x should be m1, m2. Then you go straight to the data sheet, right? Check the equation where you'll get f and m1, m2. There's only one equation. Is f equals to g m1, m2 over r squared. But now, what are you supposed to do after identifying that equation? Manipulate the equation in such a way that your subject of the formula should be what? F, and then x should be m1 what? M2. So I have done that. The subject of the formula, which is y, is f, and then m1, m2 is our x, which means that g over r squared represent what? The gradient, or the gradient of this graph represents g over what? Over r squared. Ne? So let's say you calculate the gradient, right? So how are you going to calculate your gradient? Your gradient, you need how many points? 2 points. Hence, you are given 2 points in that graph. So gradient will be change in f over change in m1, m2. Okay? So change in f will be f final minus f what? Initial. m1, m2 final minus m1, m2 what? Initial. This is how I will calculate my gradient. Okay? So f, I'm using those 2 points. Okay? What is my f final? F final is what? Is 5 times 10 to the power what? 3. F initial, it's what? It's here. At the origin is what? Is 0. Then product of the masses final. Product of the masses final, it's 1.2 times 10 to the power what? 4, right? Then initial product of the masses, it is 0. Then we'll get our gradient here. So you can also calculate at home. Check what you get. Let's calculate. I'm having 5 times 10 to the power 3 minus 0. So it's 5 times 10 to the power 3. Times 10 to the power 3. Divide that by 1.2 times 10 to the power 4. Right? So here, what am I having? I'm having, I hope we are getting the same answer, but I'm having 4.17 times 10 to the power 1, 2, 3, 4, 5, 6, 7 times 10 to the power 7. Is it to the power 7? Let me double check here. It's 5. So exponent 3 divided by 1.2 exponent 4. Yes. So here I'm getting 4.17 times 10 to the power negative 1, 2, 3. Oh, so here should be what? Negative what? 7. Okay. So that is the gradient. Okay. So now I have the gradient. What am I going to do with this gradient now? Right? What I know is that gradient represents G over R squared. Represent G over R squared. Right, so our gradient represents what? G over R squared. What is our gradient? It's 4.7 times 10 to the power negative 7. What is our G? 6.67 times 10 to the power negative what? 11 over what? Over R squared. Then your R squared will be 6.67 times 10 to the power negative 11 over 4.7 times 10 to the power negative what? 7. Then you need to find the square root of that. Then you'll be able to get the distance between the centers. Okay? You will be able to get the distance between the centers. So I'm having 5, not sorry 5, but 6.67. 6.67 exponent negative 11. Divide that by 4.7 exponent negative what? 7. All right. So here I'm having 0.000, which is actually that is R squared. So the square root of that is, so the square root of that is 0.01 meter. Right. That will be the distance between the centers. All right. So this graph is very, very important, learners. So it shows the relationship between the force and the product of the masses. The relationship from the law itself, force is directly proportional to the product of what? Of the masses. So showing that relationship using a graph, you can see there's a straight line starting from the origin. It shows that F and M1, M2, they're directly what? Proportional. But again, let's interrogate the graph. There's a dependent variable, there's an independent variable, there's a controlled variable. There is a physical quantity represented by the gradient of what? Of the graph. Okay? And you can see the gradient of the, obvious, you are aware, right? That the gradient of the straight line does not change. So at each and every point, right? You should know that the gradient does not change. So the gradient, but in this case, represents G over R squared. So at this point, A, point B, point C, G over R squared here is equals to G over R squared here. G over R squared at B is equals to G over R squared at what? At C. Because gradient of a straight line does not change. It remains constant. Okay. Then a relationship between, let me just check here. Oh, before that, there are questions where now you have to use proportionality, okay? For example, this one, right? For the two objects, each of them must m placed at a distance r apart. The gravitational force that they exert on each other is what is B. Ne? So yeah, it is going to be what B, right? If one of the masses it is going to be F, sorry. If one of the masses is now doubled, gravitational force will also be what? Be doubled. Why am I saying that? It's because F and product of the masses is directly what? Proportional. So you can prove that. So you are having M1 and M2, right? M1, M2, okay? Right? Then the distance between their centers is what? Is R, right? And then the force they exert on each other is what? Is F. In other words, F here will be G M1 M2 over what? Over R squared. But now what are they doing? The distance now is what? So not the distance, but one of the masses is what? Is doubled. So how are you going to work with that? Now you need the new F. F new, right? So I'm having G, which is still G. It's a constant, right? And one of the masses is, one of the masses is now doubled. So I can double M1 or M2. It's up to you. That won't affect the answer, right? So twice M1, M2 is still M2, R is still R. So what am I having here? I'm having twice G M1, M2 over R squared. But remember, this is F, right? Hence here I will just say 2 what? 2F. So if one of the masses is doubled, the product of the masses is doubled, what will happen to F? F is also going to be doubled. Why is that the case? It's because F and product of the masses are directly what? Proportional. So if one of the masses is doubled, even your F will be doubled. Why am I saying that? It's because the relationship between F and the product of the masses is directly what? Proportional. So if one of the masses is doubled, it means that the product of the masses is doubled. And if the product of the masses is doubled, what about F? F is also going to be what? Doubled. Why? Because the relationship between those two physical quantities is directly what? Proportional. Right. Let's move to the next one. Now looking at the relationship between gravitational force and the distance between the square, actually, the square distance between what? Between their centers. Okay? Right? So what is the relationship between what? F and product of the masses? Let's start here. So between F and R squared, right? What will be the relationship? So you have F equals to G M1 M2 over R squared. Okay? So you are not changing G M1 M2, but what is your independent variable here? Is R squared. So we are changing R squared. So let's say here it's 1, here is 2, here is what? Is 3. But 1, 2, 3 is not R, but it's R squared. So your dependent variable is F, your independent variable is R squared. It's what I have according to this graph. I'm not having R. So if they can ask you what is the dependent variable here, it should be force, which is F. What is the independent variable here? It's not the distance. No, it's not R, which is the distance, but it's what? Is the square distance. It is the square distance, which is your what? Your R squared. So this is your R squared, which is 1. And then what is R squared here is 2. What is R squared here is what? Is 3. Okay. Then I want to find out what happens to F if I increase R squared. Okay. Now I'm going to use those values of R squared. Okay, so what am I having here? Right, what am I having here? I'm having GM1 M2, okay, which is still what? G M1 M what? M2. But your R here is what? It's your R squared is what? It's 1. So for your F1, we are just having what? G M1 M2. Okay? Let's move to F2, which is G M1 M2 over R squared. G M1 M2 is still G M1 M2, so nothing has changed. But what are we changing here? It's R squared. Now the R squared is what? Is 2. Okay? So what am I having here? I'm having F. So I'm not just having what? Yeah, here I'm having 1 over 2 G M1 M2. Right? Okay? Then let's move to F3. G M1 M2 over R squared. It's still G M1 M2. It's not changing, but your R now is what? Is 3. So I'm having what here? 1 over 3 G M1 M2. So check what is happening here. As you move from from F1 to F3, what is happening? Right? Here we're having GM1 M2, but here we're having half of GM1 M2. Even your 1 over 3 is less than your 1 over 2. So what is your 1 over 3? Your 1 over 3, it's what? It's 0.33, which is less than 0.5, which is your 1 over 2. All right? So what is happening to F? This is your F, right? What is happening to F? What is happening to F? What is happening to F when you increase R squared? What is happening to F when you increase what? R squared. You can see F decreases. Here, the coefficient is 1. Here it's 1 over 2. Here it's 1 over 3. So you're moving from 1 to 1.1 over 2 to 1 over 3. So it's from 1 to 0.5 to 0.33. So you can see when I increase R squared, what happens to F? F decreases. So your graph, because of this R squared, your graph will be what? A curve. Something like this. Okay, it's going to be what? A curve, right? So this is the graph that shows the relationship between what? Between F and R squared. This is the graph that shows the relationship between F and what? And R squared. Now, let's look at F and the inverse of R squared, right? I think this should make sense to you, okay? So here I was having F and R squared, okay? I was having F and R squared. You can see when I increase R squared, right? What happens to F? F decreases. And this is based on the law itself, right? It says that force is inversely proportional to the square of the distance between their center. So it's inversely proportional. So in other words, when you increase your R squared, what should happen to F? F should what? Should decrease. And we are seeing that on those values, even when it comes to plotting those values on what? Or those points on what? On the graph. You can see that when you increase your R squared, what happens to your F? F will what? Will decrease. But now, what am I looking at when it comes to this part now? When it comes to this part, right? I'm looking at what now? F and the inverse of R squared. What should come to mind? Between F and R squared, you can see the relationship is inversely proportional, right? But now, between F and the inverse of R squared, the relationship, like it or not, should be directly what? Proportional. You can even prove that by calculations. Right? You can even prove that by calculations. The relationship between F and R squared is inversely proportional. That is based on the law itself, right? F inversely proportional to the square of the distance between what? Between their centers. So you can even prove that using what? The values there, and then plot those values on the graph. You'll see when R squared increases, your F will what? Will decrease. But now, what are we looking at? We are looking at F and the inverse of R squared. So we are expecting the relationship to be directly proportional since F and R squared is inversely proportional, right? F and R squared inversely proportional. But what about F and the inverse of R squared? The relationship will be what? Directly what? Proportional. So you can prove that. Now let's look at this graph. Okay. What am I having as my dependent variable? It's F. So this one is the dependent variable. Dependent This is my dependent variable. Then what is my independent variable? It's not r squared, but what is given here is this 1 over r squared. So this is going to be what? The independent variable. So now let's prove if this is true, that when the inverse of r squared increases, f also increases with the same factor. We can prove that, okay? So let's use this graph. I'll just give you these values, right? So let's say your r squared here is 1. 1 over r squared is 1. 1 over r squared is 2 there. 1 over r squared is what? Is 3, okay? So let's check what will happen to f when 1 over r squared increases. Remember, your independent variable is 1 over r squared. So let's check what will happen to f if we increase 1 over r squared. Okay? So I'm having f equals to what? G m1 m2 over r squared. Okay? So this is the same as G m1 m2 multiplied by 1 over r squared. It's the same thing, because I'm multiplying that gm1 m2 by 1, which is the same as gm1 m2 over r squared. What is changing here? It's 1 over r squared. Okay? So I'm looking at f equals to what now? gm1 m2. What is my 1 over r squared? It's 1. So what am I having here is gm1 m2. Okay? Let's move to the second one. F equals to g m1 m2 over r squared, or m1 m2 times, is the same thing as 1 over what? Over r squared. Ne? Equals to, this is g m1 m2. Now, what is my 1 over r squared now? My 1 over r squared is what? Is 2. Right? Then what am I having here? I'm having twice g m1 m2. So I was having g m1 m2 for the first one, where my 1 over r squared was 1. Now my 1 over r squared is 2. What am I having? I'm having twice g m1 m2. Now, let me move to the next one. Right. So we're moving to where 1 over r squared is 3. So it's f. So this is your f1. This is your f2. This is f3. F g m1 m2 times 1 over r squared. Okay, which is g m1 m2 times what? What is my 1 over r squared now? Is 3. This is going to be what? 3g m1 m what? m2. So check something here, right? When 1 over r squared increases from 1 to 3, what happened to f? F increased by what? 1, 2, 3. You can see f also increased by the same factor. Okay? So it shows that the relationship between f and the inverse of r squared is directly what? Proportional. So what happens to f if 1 over r squared increases? F also increases by the same factor. We can see that initially my 1 over r squared was 1. What was my f1? 1. The coefficient there is what? It's 1. My f2, 1 over r squared was 2. What was my f2? Also 2, right? 1 over r squared was 3. Then what was my f? It was also what? 3. So you can see that as 1 over r squared, the inverse of the square of the distance increases, what happens to f? F also increases with the same factor. So, hence we say the relationship between f and the inverse of the square distance between the centers is directly what? Proportional. But between f and r squared, the relationship is inversely what? Proportional. But between f and the inverse of r squared, the relationship is directly what? Proportional. Right. So already we have talked about the dependent variable, independent variable. Now, let's look at the gradient. The gradient of this graph is a straight line. We can talk about the gradient. But here we can't talk about that because the gradient, because this is a curve, the gradient keeps on what? On changing, right? So we can't dwell much on the gradient when it comes to curves. Ne? But when it comes to a straight line, then we can talk about what? The gradient, because we know the gradient there is what? Is constant, right? So there is a physical quantity represented by the gradient of this graph, okay? So how are we going to get that? Okay? How are we going to get that? Ne? The physical quantity represented by the gradient of this graph. Okay? So, what are we having? It's a straight line, equation of a straight line. It's y equals to mx plus what? Plus c. Y equals to mx plus c. Then your y should be what? F. Your x should be 1 over r squared. Then the equation where you have f and 1 over r squared, it's f equals to g m1 m2 over r squared. So what am I supposed to do here? Manipulate this equation f equals to g m1 m2 over r squared in a form of y equals to mx plus c. My c, obvious, because the graph starts from the origin. My c here will be what? Will be 0, right? So my y should be f. And then my x should be what? 1 over r squared. So it's what I need to do here. Manipulate that equation in the form of y equals to mx plus c, making sure that your y is f and then your x is 1 over r squared. So let me do that. Already you can see y is f, so there's no need to change that. Ne? So now what I need to find out, it's x, which is 1 over r squared. So it's f equals to what? G m1 m2. Multiply that by 1 over r squared. This is y equals to mx. You can see my x here is what? It's 1 over r squared, which is what I have here. Okay? My y is what? Is f, which is what I have there. It means that the gradient of this graph represents what? Gm1, m2. The gradient of this graph represents what? Gm1, m2. So you can use this gradient to get what? The mass. So if we are told that these objects, they are identical, right? If we are told that the objects are what? Are identical, obvious, you'll be able to get what? The mass using what? The gradient. Okay? So that is very, very important. So you'll say gradient equals to gm1, m2. The value of the gradient, then you know the value of g. Then when it comes to m1 times m2, you will say m squared because they are identical. And then solve for m, you will be able to get what? The mass of what? Of those, one of each, of those identical what? Objects. Okay? That is very, very important. Again, for the two objects, each of mass m placed at the distance r apart, the gravitational force is this. Okay? Now the distance is doubled. How will that affect f? Or what will be the magnitude of what? Of f. So this is your original f is g m1 m2 over what? Over r squared. Then now you have your new f. Your new f, you are told that the distance is what? Is doubled. But g is still g, m is still m, even m2 is still m2. But now the distance is doubled. They are not saying r squared is doubled. The distance, when we talk of distance, in this case, we are talking about r. So the distance is doubled. So r is doubled. So I can say twice r because r is what? Is doubled. But according to the equation, it should be what here? All squared. Okay? So what am I having? I'm having g m1 m2 over 4 what? R squared, right? Which is the same as what? 1 over 4 gm1 m2 over what? Over r squared. But let's not forget that this gm1 m2 is this one, which is f. So it's 1 over 4 what here? Over 4f. Okay, so here we are just working with proportionality. All right, if now the distance is doubled, what will be the new magnitude of what? Of f, right? So I don't think that should be difficult. You have the original f as f equals to gm1 m2 over r squared, but now you are told that the distance between those two objects, it's what now? It's doubled, right? So what is being doubled is not r squared, but is r, right? Hence, when it comes to this equation, I said what is being doubled is r, so it should be what? Twice r. If they said to us this r is increased by the factor of 4, I was going to say 4r, but all squared according to the equation, then solve that, then we'll be able to get what? The new magnitude of what? Of f. Okay, so here we are dealing with the proportionality. Now let's deal with calculations, right? So you can use this equation f equals to gm1 m2 over r squared to calculate the gravitational force, to calculate one of the masses, and also to calculate the distance between the centers, right? But they won't ask you to calculate g, capital letter G, small capital letter G, right? Which is gravitational constant. It is there on our data sheet, okay? Then we'll explain that. We'll explain the difference between f gm1 m2 over r squared and g equals to gm over r squared. So I will explain that. But for now, let's focus on what? On f equals to gm1 m2 over r squared. Very, very important. We'll move to g equals to gm over r squared so that you'll see the difference, right? Then, now calculations, not difficult at all because we have the equation. We expect all learners to get marks when it comes to calculations for this equation. But please, learners, read statements with understanding. Already I've explained the issue of the distance. It's not just any distance that you see. The statement must mention that this is the distance between the centers. Then if they're saying that, or they can show that in a form of a diagram, right? So if they're saying that, it means that you have your R. But in a scenario, this first scenario that I gave you, where you are having what? The earth and the object, all right? Object A, but now the distance that was given was from the surface of the earth to the center of that object. Ne? So you can't say you are given R, right? R, remember, is from center to center. So please be careful, learners, when it comes to the issue of distance. It's where learners lose marks. Okay? It's where learners lose marks. And again, learners, you shouldn't lose marks again. Mass should be in kilograms, right? If you are given mass in grams, remember this is not chemistry, this is physics, right? So in chemistry, your mass is in grams, right? That is the SI unit when it comes to your chemistry. But when it comes to physics, the mass should be in what? In kilograms. So if you're given mass in grams, you have to convert those grams to kilograms. If you're given distance in centimeters, you know, in millimeters, right? So you can't just use those millimeters as they are. Or if you're given the distance in kilometers, you cannot use those kilometers as they are. So we need distance in meters. So you must be able to convert centimeters to meters, kilometers to meters, you know, millimeters to what? To meters. Then you'll be able to get your calculations correctly. All right, so that is very, very important. Right, but again, the issue of copying the equation as it is from the data sheet, right? You cannot lose marks just for doing that. Copy the correct equation from the data sheet and then substitute from that equation, right? So here, calculate the gravitational attraction between the Earth and the Moon, right? And we're given the mass of the Earth at 6 times 10 to the power 24 kilograms, and we're given the mass of the Moon, okay? And then the distance between their centers. Okay, let's assume that this is the distance between what? Between their centers. So let's calculate the gravitational force that the Earth exerts on the Moon. Okay, the equation is F equals to gm1 m2 over r squared. What is our G? 6.67 times 10 to the power negative 11, and we're getting that from the data sheet, right? Not from our heads, right? Then what is the mass of the Earth? The mass of the Earth is given as 6 times 10 to the power 24. And then what is the mass of the moon, which is M2? It's 7.35 times 10 to the power 22. And then what is the distance between their centers? The distance between their centers is 3.8 times 10 to the power 8. But let's not forget a square. Most learners, they will also lose marks when it comes to that. So please, let's not rush when we are dealing with this equation. Okay, so there's a question here. So what happens if you are not given the radius, right? Guys, when you look at our data sheet, you are given, right? You are given what? The mass of the Earth as 5.98 times 10 to the power 24 kilograms. You are given the radius of the Earth, which is from center to the circumference, from center to the surface of the Earth, right? You are given that, okay? So if one of the objects is the Earth, it's like you're given all the information for the Earth, right? So if one of the objects, for example, in this case, one of the objects that we are dealing with here is the Earth, already we have the mass of the Earth, right? Already we have the radius of what? Of the Earth, okay? So if it's not the Earth, maybe it's another planet. For example, planet X, planet Venus, right? Guys, the examiner does not have a choice but to give us what? The radius of that planet, the mass of that planet. But if one of the objects is the Earth, there's no need for the examiner to give that to us because we have that on our data sheet. I hope it's making sense, right? If one of the objects is the Earth, we are given the mass of the Earth from our data sheet. We are given the radius of what? Of the Earth from what? From our data sheet. That is very, very important. But if it's not the Earth, maybe it's another planet, planet X, Y, Z, it doesn't matter. So the examiner must give us what? The radius of that planet. The examiner must give us what? The mass of that planet. That is very, very important. Okay, so I hope I've answered the question. So what we got here is 2.03 times 10 to the power 20 watt newtons. So this is the force exerted by the Earth on the moon, right? This is the force exerted by the Earth on what? On the moon. So this is the magnitude, okay? So here, if they are looking for the distance, not the distance, but for the direction, right? The law says each body in the universe attracts every other body. So there's attraction, there's force of attraction here, okay? So the force exerted by the Earth, right? The force exerted by the Earth on the moon, right, is 2.03 times 10 to the power 20 newtons. So this will be 2.03 times 10 to the power 20 newtons towards the Earth. Okay, if this is the force exerted by what? Earth on moon. Earth is, so it's on what? It's on moon. So here it's going to be what? 0.3 times 10 to the power 20 newtons towards what? Towards the Earth. Or you can just write attraction. I think it's still fine. Because if everybody in the universe attracts every other body. Okay, so it's just, you can just say it's what is attraction, right? Then another thing, look at number 2. Compare this to the force of attraction between 60 kilograms adults standing 2 meters apart. Okay, fine. Maybe before we compare, right? What you need to understand here, right? The force exerted by Earth on the moon will be equal to the force exerted by the moon on Earth, but acting in opposite what? Directions. That is application of Newton's third law, right? So the force exerted by what? By the Earth on the moon will be equal to the force exerted by the moon on what? On Earth, but acting in opposite what? Directions. So there is application of Newton's third law there. force exerted by Earth on Moon will be equal to force exerted by Moon on Earth, but acting in opposite what direction. So application of Newton's third law. So here they're saying compare this to the force of attraction between the 60 kilogram adults standing 2 meters apart. Adults, right? So here the equation is F equals to gm1 m2 over r squared. So it's 2 adults, all right? I assume based on the equation, or because of there's m1 m2, there's no m3 there, all right? So G is 6.67 times 10 to the power negative 11. This is adult 1 with a mass of 60 kilograms. This is adult 2 with a mass of what, of 60 kilograms. And then what is distance between their centers is 2 meters, but this should be 2 to the power 2 because of that r squared. Then the force will be 60, not 60, but at 6 times 10 to the power negative 8 what, newtons. Okay, so here we are just calculating F, and we're giving the values. And please, learners, be careful. It's not always the case that we'll be calculating F. In other scenarios, we'll be calculating what? One of the masses, the distance between the centers. Guys, even if it's like that, please copy the equation as it is, because some learners will manipulate the equation first and then substitute from the manipulated equation. We don't give marks for the manipulated equation. We give marks for equations from the data sheet. So copy that equation as it is, even if they want you to calculate m1 or m2 or r squared. But the equation is F equals to g m1 m2 over r squared. Please, learners, let's do that, okay? Let's not manipulate the equations, because we are going to manipulate them wrongly. And if it's manipulated already, no marks for that equation, okay? Right, so please be careful. So just copy the equation as it is from the data sheet, and then from there, just substitute from the equation. Substitute whatever you have, and then from there, you'll be able to get what you are looking for, okay? Right. So again, the issue of Newton's third law here comes in, all right? So there are 2 adults here. It's, you can say adult A and adult B, right? So what you need to understand is that the force exerted by A on B is equal to the force exerted by B on what? On A. So, but acting in opposite what direction? So the force exerted by A, or adult A on adult B, is 6 times 10 to the power negative 8 newtons. Even the force exerted by adult B on A will be 6 times 10 to the power negative 8 newtons, but in the opposite what direction. So what happens when we are not given one mass? So if you are not given one mass, obviously they will ask you to calculate the other mass, right? So they don't have a choice. They have to give you what? F, G, R squared, and M2, for example, so that you'll be able to get that mass, right? So you won't find a situation where we are having 2 unknowns. If you're having 2 unknowns, obviously we've been dealing with Newton's second law here, right? Like it or not, somewhere, somehow, you will be asked to solve equations simultaneously, because you cannot get physical quantity without solving equations simultaneously. I think so, right? So please be careful. If it's more than 2, or sorry, if it's more than 1 unknown, so something must be done. Somewhere, somehow, you have to solve equations simultaneously. So you've seen that when it comes to Newton's second law. Okay. Then this is another activity. Gravitational force exists between the sun and the earth. Sun and the earth. I'm giving the earth already. I know the mass. From the data sheet, it's what? 5.98 times 10 to the power what? 24 kilograms, right? I know the radius of the earth. It's what? It's we'll check that from what? From the data sheet, ne? So it's 6.38, if I'm not mistaken, times 10 to the power 6 what meters. Okay, so that is the radius of what? Already I know that, if one of the objects is the earth. Okay, then state Newton's law of universal gravitation in weights for 2 marks. So everybody in the universe attracts every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Not between them, but between their centers. So don't confuse Newton's law of universal gravitation with Coulomb's law. I know some of you are busy with Coulomb's law, you are busy with electrostatics, but let's not confuse the two laws. Please, let's not do that, because sometimes the question will be on Newton's law of universal gravitation, but Elena will write an equation of Coulomb's law, right? F equals to K Q1 Q2 over R squared. No, there we are dealing with charges. But when it comes to Newton's law of universal gravitation, we are dealing with what? With masses. So it's G M1 M2. But that other side is K Q1 Q2. So you can't have, there's no way that you can have an equation where you're having K M1 M2 of R squared. Never. K and G, those are two different what physical constants. Okay, so please be careful when it comes to that. So the mass of the sun is 330,000 times greater than that of the earth. The distance between the centers, very, very important, between the centers of the sun and the earth is 1.38 times 10 to the power 9 meters, right? So you are given what? Mass of the earth. You also have the mass of the sun, because they are saying the mass of the sun is what? It is 330,000 times greater than that of the earth. So you just multiply the mass of the earth with 330,000, then you will be able to get the mass of what? Of the sun. So we are given that. Okay. Then they want us to calculate the gravitational force that the sun exerts on what? On the earth. Okay. So let's check. The equation, F equals to Gm1 over R squared, okay? Then what is G? 6.67 times 10 to the power negative 11. Mass of the earth, we have that on our data sheet. And then this is the mass of the sun. The mass of the sun. We are told that the mass of the sun is 330,000 times greater than that of this of what? Of the earth. Hence, we multiplied 5.98 to the power 24 by 330 thousand. Then the distance between the centers, we were told that this is the distance between the centers. It was 1.38 times 10 to the power 9, right? And it was given in meters, so there was no need for us to convert. And then all squared. Then the force that exerted by the sun on the moon, on the earth, it's going to be 4.13 times 10 to the power 26 watt Newton. So that one was straightforward. Okay. Then the other question here, how will the gravitational force that the earth exerts on the sun compare to the answer to question 1.2, right? Only greater than, less than, or equals to give the reason for the answer. The force exerted by the sun on earth will be equal to the force exerted by what? Earth on what? On the sun, but acting in opposite what? Directions. So if they say give a reason, obviously you have to use Newton's third law to do that. So you can see here they said Newton's third law is what? Is obeyed. So hence they're saying it's equal to the magnitude of the force exerted by the sun on earth will be equal to the magnitude exerted by the what? By the earth on the sun. But remember, those two forces, because they're vectors, so they're acting in opposite what? Directions. So why is it equal? Newton's third law is being obeyed there. So yeah, there's application of Newton's third law. Right. Now let's move to acceleration due to gravity. All right. Acceleration due to what? To gravity. Okay. So acceleration due to gravity on planet Earth, we have that. I hope we are aware. We have acceleration due to gravity on what? On planet Earth, which is 9.8 meters per second squared downwards. Okay. So when it comes to acceleration due to gravity, okay, how do we calculate acceleration due to gravity? Okay. So we know that weight is given by mg. All right. Gravitational force is given by Fg m1 m2 over what? Over r squared. But we know that weight is gravitational force. Okay? So where there is gravitational force, I can substitute by what? By weight. Ne? So weight is gravitational what? Gravitational force. Weight is mg, and then this one is what? G m1 m2 over what? Over r squared. G is equals to G m1 m2 over what? Over r squared. I'm dividing by m. So when I divide by m, this is the same as what? Divide by m, divide by what? By m. Then this will be the same as 1 over what? 1 over m. All right? So this and this cancels. Then at the end, what are you going to have? You're going to have g equals to g m over what? Over r squared. Okay? Yeah, equals to g m over what? Over r squared. So that g equals to g m over r squared. Please be careful, learners here. This is acceleration due to gravity. Guys, what you need to understand, right? As you move to another planet, right? Gravitational acceleration changes. On planet Earth, it's it's 9.8 meters per second squared, but on planet Venus is different. Okay, so hence here you'll be asked to calculate, you know, gravitational acceleration or acceleration due to gravity on planet X, planet Y, planet Venus, for example, right? Because gravitational acceleration changes as the mass of the planet changes and also the radius of the planet changes. Okay, so when you look at this equation, g equals to gm over r squared, which is this one, all right? So this is gravitational acceleration, which is measured in meters per second squared, and then this is the constant, okay, gravitational constant. M, guys, is mass of the planet, mass of planet. So because we'll be calculating acceleration due to gravity on that planet, not acceleration due to gravity on a person, but acceleration due to gravity on what? On that planet. So this m is mass of the planet. If you are dealing with the earth, it will be mass of the earth. If you are dealing with what? With planet X, for example, it will be mass of planet X. So this m is not your mass, but it's the mass of the planet. Which planet? It depends. It's maybe it's planet what? Mars, planet Venus, planet Earth. So it depends. Planet Y, Z, it doesn't matter. But m is the mass of the planet. Okay, so m is the mass of the planet. Let's not forget that. M is the mass of the planet that you are dealing with. If you are dealing with planet Mars, planet Earth, m will be mass of the planet, right? What about d? D is not the distance, but it is the radius. D is the radius of that planet. If you are dealing with what? With planet Earth, D or R will be the radius of the Earth. If you are dealing with planet Mars, right? M will be mass of Mars or planet Mars, right? And then your D, your R will be what? The radius of planet what? Of planet Mars. That is very, very important. So when it comes to this equation, please learners, let's understand this. M is the mass of the planet. If it's the Earth, it will be mass of the Earth, right? R is the radius of the planet. If it's planet Mars, then that will be the radius of planet Mars. I hope it's making sense. So let's not confuse this equation with this one, right? Here is mass of object 1, mass of object 2, distance between their centers. But here is not the distance between their centers. Here is the radius of that planet that we are dealing with. Remember, we are calculating acceleration due to gravity on that planet. Planet Earth, acceleration due to gravity on planet X, acceleration due to gravity on planet Mars, acceleration due to gravity on planet Venus, acceleration due to gravity on planet Z. So m is the mass of that planet. R is the radius of that planet. I hope it's making sense. When we are calculating acceleration due to what? To gravity. Okay. Then we can even talk about the relationship gm over r squared. Okay. So the relationship between g and what? And mass is directly what? Proportional. G and mass of the planet is directly what? Proportional. Between g and the inverse of one, the inverse of what? The radius, right? The relationship is also directly what? Proportional. Okay? So we can even talk about the relation from the what? From the equation itself. Okay? So if you increase mass of the planet, right? Moving from planet A to planet B. Let's say the mass of A less than the mass of B. Then we are moving from a smaller mass to a bigger mass. What will happen to what is this acceleration due to gravity? It's also going to increase, provided the radius is the same. All right. So G and M at constant R, right? Directly proportional. G and the inverse of the radius squared, ne? A relationship is also directly proportional at constant M. So those are the things that you need to be careful about when it comes to this. All right. So again, the issue of proportionality. So let's look at this equation. So planet X has a mass twice the mass of the Earth and a radius 1.5 times that of the Earth. If the acceleration due to gravity on the Earth is G, acceleration due to gravity they're saying is G. And we know that G is given by what? Gm over r squared. Ne? Then the gravitational acceleration on planet X will be what? So we are told that we are looking for what? Acceleration due to gravity on planet X. Then what are they saying to us? G is G. It's the constant, right? Then we are told that the mass of planet X is twice the mass of the Earth. So this is the mass of the Earth. So it's going to be what here? Twice the mass of the Earth. That is the mass of planet X. Okay? And we are told that the radius, remember when it comes to this equation, M is the mass of the planet, R is going to be what? The radius of that planet. Okay? Then we are told that the radius of planet X is it's what? 1.5. Right? So it's 1.5 times that of the Earth. So if they say 1.5, I'm looking at 1.5, which is the same as what? 3 over 2. Ne? So it should be 3 over 2. It's 1.5. Ne? So radius is 3 over 2r. But remember, it's all what? All squared. So what am I having here? Is twice gm over 9 over 4r squared. Okay? I hope you are following. So I'm having 2 over, okay, let me just do this. So this is the same as 2, yes, 2 over 1 times 4 over what? Over 9. Okay? Which is g what here? Which is gm over r squared. So I'm having what here? 2 times 4 is 8 over 9. G m over r squared. Okay? Then because it's one of, yeah, it's yes, I think this is what we have. Ne? Do we have this as one of the options? Yes, we have it. It's one of the options. Yeah. So this is how we have to do it. Ne? So you are told that acceleration due to gravity on planet Earth is g, and we know that g is m1. It is gm over r squared. Then we are told that the mass of planet X is twice the mass of the Earth. So hence there's 2 there. And we are told that the radius of planet X, it's 1.5 times that of the Earth. So 1.5 is 3 over 2. But remember, it's 3 over 2 are all squared. Hence here I'm having 3 squared, which is 9, 2 squared, which is what? Which is 4, which is the same as 2 times 4 over 9, which is 8 over what? Over 9. So the correct answer there is what? It's A. So it's proportionality, learners. Okay? That is acceleration due to what? To gravity. So calculations, here they were trying to prove that acceleration due to gravity on planet Earth is 9.8. How did they do that? The equation is there on your data sheet. Is G equals to gm m over d squared. Okay? Then G is 6.67 times 10 to the power negative 11. And then 6 times 10 to the power 24. Here, actually, they're supposed to use 5.98 times 10 to the power what? 24. Right? And then what is radius of the Earth? Because this d or r squared, when it comes to this equation, is the radius of the Earth. Right? Then what we have there is 6.68 times 10 to the power 6 all squared, What is this? It's from the data sheet, which is the radius of the Earth. And then here they got what? 9 point, I think it's 7 something, which is approximately what? 9.8. Right. Okay, so there's a question here. If there's by chance needed to explain an answer, is it valid to refer to previous laws? Yes, you have to. For example, the one of force exerted by sun on the earth. The force exerted by sun on earth will be equals to the force exerted by earth on sun. Where are we getting that from? From Newton's third law. Okay, so obviously you are referring back to what we have done before, or the laws of physics that we have done before. So obviously you will be required to do that sometimes. Okay, then so here they were proving that acceleration due to gravity is what? Is 9.8. So I think learners for today, let's stop here on acceleration due to gravity. Okay, calculation. All right, and then next week we are going to look at what is the difference between the mass and the weight. Okay, and also the meaning of weightlessness, right? And then do more calculations on Newton's law of universal gravitation, and also acceleration due to gravity. I think for today we have done enough. I think if I can move again from this, I think I will be confusing you. So thank you so much, and thank you for for watching this lesson. See you next Friday. Thank you so much. Bye bye.